Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm Shubhendu Lahiri, and it's my great pleasure to introduce Brian Hackett, who was interning with Shaz Qadir and myself in the Software Reliability Research Group this summer. Brian is a PhD student at Stanford, and he's an MSR Research Fellow. And this is Brian's fourth internship at Microsoft. And so he's going to talk about his project this summer on using static analysis on the Ntfs file system. Brian.
All right. Thanks. Hey, is it working? Okay. Yeah. So this summer I was mostly developing and using the Havoc tool, basically for looking for synchronization-related errors in Ntfs. It just has a little bit of background. So Ntfs, which is the NT file system, is the main file system used in Windows. As a result, it's fairly big. It's been around a while, and it's very complex. It has a lot of features, and is fairly highly tuned. Partly as a consequence of this, there are a lot of properties within Ntfs that that Ntfs code really needs to follow. That if the Ntfs code does not follow these properties, they can get all sorts of runtime errors. Deadlocks, leaks, corruption, and just generally crashes, very bad behavior. And the problem here is that since these properties are specific to Ntfs, a fairly small code base relative to the size of Windows itself, that we don't have much checking support for these properties at this time. That the more general purpose tools like prefix and prefast will not be looking for Ntfs specific errors, and a lot of the tools that you can actually tune to particular properties don't have the expressive power we need for these fairly complex issues. So we're interested in how we can actually check these. And what we want to do is that we're going to be using this tool Havoc, which has been developed here at MSR. And it's a fairly general purpose contract checker for C, which is just languages of preconditions, postconditions, and loop invariants. And it's plugged into a very powerful backend. There's this technology Boogie, a verification condition generator, and Z3, a theorem prover. And these combine really to give us exact reasoning about the possible behaviors of a loop-free piece of code, which is really pretty important for Ntfs, which is very complicated control flow, very complicated heap manipulations going on, and it also has a number of functions that are several thousand lines long, so we need to be able to analyze those as well. Unfortunately, this technology can do this, so we can actually plug it in to these huge functions in Ntfs and exactly analyze what they're doing. But we need the preconditions and postconditions. We need to understand what the property is that we're checking. And so what our plan is that we'll just take these Ntfs properties and we'll map these down into Ntfs-specific annotations. Just construct a new annotation language that describes the properties that we're checking, and then but give these a nice, precise semantics. We represent them in terms of the lower-level Havoc annotations that will let us check them using this general-purpose checker with all this power behind it. So a general summary of what we did is that we used Havoc to check a number of properties within Ntfs, related to resource leaks primarily, and quite a few data races, as well as teardown races where one thread is trying to access an object, one other thread is trying to delete it, which can be especially nasty. We found about 50 bugs, which have been mostly confirmed by the Ntfs developers. We're looking to pick up the tool there, to pick up the annotations as well as the checker. And in terms of the overall effort required here is that we had several hundred lines both to specify the annotation languages for describing these properties, for adding manual annotations to special functions in Ntfs that are doing complex things, as well as several thousand inferred lines of annotations, which we need, because there are several thousand functions, actually about 1,500 functions in Ntfs. This took up the bulk of the internship, but this includes time both for developing the tool as well as ramp up for actually understanding the code base, because I had no familiarity with it before beginning this internship. So what we came up with was this nice little roadmap for how we can actually take this tool and apply it to these properties to actually get some checking for these complex system-specific properties. What we'll do is we'll write our annotation language for the property, and then we'll add these annotations to the code, which we can do through manual annotations, inferred annotations, as well as annotations that will basically instrument at particular syntactic accesses within the code. And then we'll run our general purpose checker, which is pretty much push button. So you really have to illustrate this with an example, though. And our first main example will be a particular property in Ntfs. So here's a blob of code. If you fed this to a general purpose checker or to someone who didn't have any familiarity with the code base, this is going to be largely meaningless. They won't know what's going on. But what we can do is we'll pick out a particular property. What we'll see is that there's this reference count field. And at one point it's incremented, at one point it's decremented. This is actually a very important field because these increments and decrements have to match. If you increment without decrementing, they can get a memory leak, where basically that file will hang around in memory until you reboot your machine. If you decrement without incrementing, then you can get a use after free error. So it's really important that the code maintain this property. And this example, it looks like it does. The problem, though, is that there's this other call here, Ntfs acquire exclusive Fcb. And it turns out this call can actually throw an exception. And if it throws an exception, then the reference count will not get decremented, and this file will hang around forever until you reboot. What we're illustrating with this example is what is the information we need to be able to find this bug, because there are a number of other bugs similar to this in the code base. So what we need is we need to understand what this reference count property is, what it means to increment and decrement, and what are the rules related to this property. And second, we need to know which functions an Ntfs can throw, because we have the 1,500 functions, and a bulk of them, or the majority actually, can throw exceptions. So we'll go back to our roadmap. We have the information we need to fill in this roadmap with the information that we need to get out of the tool. We need an annotation language that describes the reference count property, what it means to increment and decrement a ref count. And we need to instrument these annotations everywhere there's actually a physical change to the field. And we need to infer which functions an Ntfs can throw. We need all this information to be able to find this bug. So we'll start at the beginning. So what does it mean to increment and decrement a ref count? Well, what we want to do is we want to add some nice little fairly intuitive annotations, just increment ref count and decrement ref count, which capture what it means to increment. So if you have a function foo, which increments without decrementing, then we want to add an annotation increment ref count of Fcb, which indicates that this actually has a net change. It'll actually increment it. But more importantly, if you don't have an annotation like this, then we want to make sure that it's actually balanced, that you didn't change the value of the ref count going out from a different value than it was coming in. And so we specified the annotations we want. How do we actually define these? And what we can do is that Havoc is going to give us some building blocks, which are basically fairly low-level annotations, which we can use to express these properties. And since Havoc is based on contracts, the main annotations are preconditions and postconditions, where requires expression is an expression that must hold at entry, ensures expression is an expression that must hold at exit. And these expressions can include more or less any C expression. Any combination of conjunction, disjunction is fully supported and completely modeled down to every last detail. We'll also add implication because it's pretty useful for writing specs. But probably most importantly is that we want to add the concept of an abstract resource to the language, to the annotation language. Because the resource will let us model the ref count. It will let us model all sorts of other properties which don't really have much explicit representation in the code. And so the idea of a resource is just an integer, and there's no fixed meaning to what it is. The only meaning is assigned by how it's used within the annotations. So you can indicate these within annotations. There's this resource name expr, which is just the value of that resource at this point, whether this is a precondition or a postcondition. And you can also have this old resource, which indicates the old value at entry, which lets you relate the pre and the post state. Like if you want to do an increment, you're changing the value by 1. And with the we'll use this to model the reference count. We'll use this refcnt resource, and we'll just stipulate that whatever value this resource has, this is the number of times the current thread has incremented the ref count. This might actually be less than the physical value if other threads are also playing around with it. But we're only doing single-threaded analysis at this point. But since we're using this to model the ref count will change as the program executes. So we need to have a way of modifying the value of a resource. And we'll have another annotation for that, which is called modifies resource. It just says that the value of this resource might be different at function exit than it was at function entry. And the dual is that if you don't have this annotation for a particular resource, it says that resource must be balanced. It must be the same at exit as it was at entry. And so if we take our modifies resource, our requires and ensures, now we have everything we need to specify what the ref count annotations are. So let's do that. So we have increment ref count here. This is just a macro. So this is a C macro that expands out to the corresponding Havoc annotations. And that will look like this. We'll say that we took the file Fcb and we modified the value of its ref count. But we're going to have an ensure saying that we know that the new value is equal to the old value plus 1. Now we'll do basically the same thing for decrement ref count. We'll have an extra requires clause here saying that the initial value must be at least 1, because you can't decrement the reference count if you haven't incremented it first. Because again, that will lead to a use after free error. And that's it for these annotations. So, but the problem though, I mean, we've defined these annotations. We haven't inserted these into the code yet. We want to add these at the physical accesses. So we want to know how do we do that? If we go back to our original example here, so let's see. So what we want is that we want to add our increment ref count annotation here, and we want to add our decrement ref count annotation here. But more importantly, we want to add these at every place in the code where the Fcb error reference count field is incremented or decremented. And our solution to this problem is that we want to use syntactic instrumentation. We want to add these annotations everywhere we see this pattern of an increment or decrement to this field. So that's what instrumentation is. It's just saying if you see a particular access in the code, I want to insert a special function call, and whatever annotations are on that function call, the checker will read those in. And you can use this for introducing state changes to the resource to add extra checks or extra assumptions about what the code is doing. It's a fairly flexible mechanism. And so with our increment ref count, we'll have this instrument increment annotation, or it's actually a directive rather than an annotation. And what this means is whenever you see an increment to some Fcb error reference count field, I want you to insert a call to instrument increment ref count. And then the other annotation, increment ref count, will actually have the desired effect of incrementing the ref count resource, which will be tracked by the checker. So, and we'll do the same thing for decrement. And you can also, it's not just increment and decrement, there's also read and write and a number of other accesses you can instrument. So what does this give us? Now we can check this property. Well, if we took some simple functions foo and bar here, which modify the reference count, we can run the instrumentation and get the annotations we want. And if we run the checker, we'll get the violations here. We'll say that here there's a path where we decremented the resource without incrementing it first. So there's a precondition violation on that decrement. And in the second call, we'll see that there's a path where they incremented without decrementing, which breaks the balancing property that we want. There's no actual annotation on bar, so it should maintain the ref count resource for all files. The problem, though, is that there are no code paths in Ntfs that actually look like this. That at every straight line code path, if a ref count is incremented, it's later decremented, like we saw earlier. Every violation of this property is due to exceptions. So we need to handle structured exception handling. What SEH is that it's a Microsoft extension to C. It's adding these try except finally blocks that let you implement exception handling in your code base as exceptions and exception handling. It's used very extensively within Ntfs because most functions can throw, but there's no real indication in the code of which functions can throw except for comments that you see on some of the most important functions. And like we said, all bugs that we found were on these paths. So it's important to understand what's going on here. So what we added to Havoc was handling for structured exceptions. So there's this may throw expr annotation, which just takes a condition that indicates where this function might throw. That if this condition holds, then the function might throw an exception. I guess, and more importantly, if this condition does not hold, then the function does not throw an exception. It cannot throw an exception. So may throw true is this function might throw at any time. You always need to treat this function like it throws. May throw false is this function never throws. And may throw false is the default, but so if you don't have any may throw annotation at all, it'll be treated as may throw false. This condition is actually pretty useful for a number of core kernel functions as well as functions within Ntfs. So something like this ex allocate pool with tag, which is one of the core kernel allocation functions, has a conditional throw behavior where you can specify a flag to tell it to throw an exception if the allocation fails instead of returning null. And we can model that exactly with this may throw annotation here. So given this may throw annotation, Havoc will check that it's correct, that there are no conditions where a function can't throw unless it's indicated via the may throw annotation. But we still need to add the may throw annotations to the code itself. And again, the NTFS is about 1,500 functions, and the bulk of them can throw. That's a huge amount of manual work to go and add these annotations. So we'll use inference. And what we'll do is we'll leverage the checking power that we have for the may throw annotation to infer which functions an NTFS can throw. And what we're exploiting here is that most functions which can throw are just may throw true. They might always throw an exception. You always need to treat them like they throw. And so what we'll do is that for any function which we can't prove can't throw, then we'll add a may throw true annotation. And then in places where necessary, we'll be able to refine the conditions to whatever precisely models what the code is doing, where it's important. So we'll do an example here. So let's take some code. So exRayStatus is the primitive kernel function to throw an exception. So we know that's baked into the analysis. We have some code here, NTFS RayStatus calls exRayStatus directly. It's just a wrapper. And then do something can call NTFS RayStatus, and do something catch can call do something. But do something catch will catch any exception that's thrown and do the proper recovery without rethrowing anything. So we want that these two functions on the left can throw, and this function on the right can't throw. But the way in which we'll determine this, we'll assume every function can't throw. And what we'll do when we have this is that now we can run the checker over it, find which of these annotations are actually incorrect. So our first function, NTFS RayStatus, we'll get the error because that calls RayStatus directly. But NTFS do something will pass because it calls RayStatus, but RayStatus is currently annotated as not throwing, so it won't treat that call as throwing. Do something catch will do the same thing. And so now we have the error in one function. We need to get rid of that annotation and convert it to may throw true. And rerun the checker. When we rerun the checker, that NTFS RayStatus is now correct, but do something is now incorrect. It calls a function which we now know can throw. So we'll do the same thing. We'll get rid of that annotation and rerun the checker, and everything will pass. I mean, this is a very simple analysis. I mean, it's been done before. I mean, it's the same analysis that's used within the Houdini checker, but it's just a nice general mechanism for leveraging any checker to do inference. But now we have everything we need. We've instrumented the increments and the decrements, and we've inferred which functions in the code base can throw. And using this information, we found about 14 bugs in NTFS where there were exceptions thrown and the reference count was not adjusted correctly. Most of these were leaks. A handful of them were decrements without increments, or rather double decrements, which could lead to use after free. We also inferred about 900 functions in NTFS which could throw, which in and of itself is very valuable information. Because I know that one of the NTFS developers was going through the code by hand, trying to find which functions can throw. And there's also some ongoing work, I believe, to try to reduce the number of functions which can throw. And we hope that this checker will be very helpful for both of those pursuits.
Is this which code base of NTFS? Which code base of NTFS?
We were all looking at Vista RTM. Yeah. We haven't updated the annotation for Win7, but it should be fairly straightforward. Let's see. But this kind of begs the question, though. We found 14 bugs. Are there any more? Did we find them all? And the short answer here is probably not. We probably found all of them, but we're not sure. It would be really, really nice to guarantee that a code base is free of a particular kind of defect, but we're not there yet. Havoc provides guarantees for code bases modulo a few big assumptions, which it needs to reason precisely about heap locations, which is a very important ability for a code base like NTFS. So we'll just go over those assumptions pretty quickly. And one of these big ones is just type safety. It's just saying, I have two pointers to objects of different types. Can they point to the same thing? In most code, this is not actually the case, but C, of course, lets you do this because C lets you do anything. So we'll say that X arrow F and Y arrow G in this example probably can't overlay. If they can't overlay, then we can prove this assertion that X arrows F equals 0, as well as anything further down in the code that might be talking about X arrows F. But again, that we don't know this for sure. We'll just assume they can't, and this is an unsoundness. There are some places where you can actually overlay structures and intentionally, and we're not modeling that behavior correctly. A second assumption, which is a little scarier, is just about side effects. That we have a similar example where we wrote 0 to x arrows f. We called some random function, and then we want to see if that value that we wrote is still there. So can bar modify x arrows f? And we have no idea. We're not. You can give mod set information to Havoc, but in general, for these large code bases, the mod sets are huge, and it's hard to tell what are the actual modify sets and what's actually relevant to the property that I'm checking. So we'll just assume that any function can't modify anything except where we explicitly indicate it, which is important for out parameters. So taking these two together, I mean, Havoc can be used to enable both checking for type safety and checking of modified sets. It's not really practical for these huge code bases just because of the huge annotation burden. So we're just going to say is that we're not giving total guarantees, but we're giving good guarantees. And we're reasonably sure that the properties that we're checking that we are finding all or all but a handful of the bugs. But more importantly is that we can find these bugs with relatively little work. I mean, we showed you with the reference count property, we had to do very little work to find those bugs. And we want to be able to extend this to other similar properties in the code base that we can also fit into this resource abstraction that we have with Havoc. And to that end is that we'll be going into a more complicated example for the rest of the talk, which is, well, we had this acquire exclusive FCB function which can throw. We're wondering, well, what's this call actually doing? Is it's acquiring the main resource on that file so that it can access that file's contents. And this resource is stored at FCB arrow resource, and it protects most data in the file. It protects its state information. It protects the contents of any streams that are sitting under it. It protects the links that are coming into it. It protects a whole lot of stuff. And we want to find data races on this because it's accessed in a very highly concurrent manner, and if you start accessing this protected data without holding the right locks, you can very easily get corruption. And there's not really much, and let's see. So what we're going to do is that we're just going to show some examples of what this resource looks like because it does not behave the way in which you normally think of a resource as behaving. So just have a straight line piece of code here. So and we want to capture all the behaviors that are being done by this code. What we have here is that first what this code is doing is that it's going to try non-blocking acquire of the file. What this will do is that it'll return either false or true depending on whether it acquired the resource, but it's not going to sit around and wait if someone else is holding the resource. If the non-blocking acquire fails, then it'll release some other things that it's holding and then call acquire exclusive FCB. Again, the same function, just passing a different set of flags that tells it to do a blocking acquire, which must either succeed or throw an exception. So this if statement correctly acquires the file. Once this if statement succeeds or finishes executing, then we'll actually go and update the state of the file, which is an operation that really does require that the file's main resource be held. And finally, that will go down and call some function Ntfs update FCB and SCB, which requires that the file also be held. It'll transitively call some more functions which can also update the file and will not do any attempt to reacquire any resource. Now, this code, I mean, as we saw with the reference count example, this code looks correct. It looks like they acquired the file correctly. It looks like the updates are being done in sync with the resource. The problem, though, is this other function, Ntfs verify and fix file record. This actually has a fairly curious side effect, which is that it can go and release every file that's been acquired up to this point in the thread. And what's actually going on is there's some behind-the-scenes work happening. This ERP context heap location, which is passed to all these functions, is storing some thread local state, including a list of which files have been acquired by the thread up to this point. It actually has this exclusive FCB list, and when you call Ntfs acquire exclusive FCB, it will both acquire the resource and thread it onto this list, so that verify and fix file record and all of its transitive callees are free to loop through that and release it if they want to. So what we want to do is that the first check which occurred before the call should pass because the file is definitely still acquired there, and the call to Ntfs update FCB and SCB should fail because the file may have been released. We think that there's a bug here. So we want an annotation language, and we want the inferred information to capture everything that we see on this slide. So let's go back to our roadmap. we need a property-specific annotation language that describes everything we've seen related to the Fcb resource, which is not just acquire and release, but also release all, as well as the requires held. And then we need to add these annotations. Then we need to add these annotations to the code. We need manual annotations for the acquire and release functions, which have fairly complex path-sensitive behavior, depending on which flags are passed in. And we need to instrument annotations that the actual physical reads and writes to the protected fields. And finally, we need to infer which annotations both require the resource be held at entry, as well as which functions might release all resources. Because in both of these cases, there are hundreds of functions within the Ntfs code base which have these possible side effects. And finally, we'll run the checker and find this bug. So let's start at the beginning again. We need some annotations. So we had our 4 properties from the previous slide. These will just be high-level annotations which are defined using macros. And in the same way in which we did the reference count, we'll also use a single resource to model the Fcb, which will represent the number of times the Fcb resource has been acquired. So requires exclusive Fcb is just requires this resource's value be at least 1, not 0. And acquire exclusive Fcb, since we need, this is going to be similar to the increment ref count that we saw, but there's some conditional behavior here where we need to attach this when variable, which indicates when the file was actually acquired by the function that this is attached to. So here's the expansion that we'll use there. It modifies the value Fcb res for this Fcb. It ensures that if the condition when holds, that we change the value by 1. And if not when holds, then it left the value alone. It didn't acquire or release the file. And release Fcb, same thing as ref count. It's just it ensures that the new value is equal to the old value minus 1, and it requires that the old value be at least 1. It's also an error to release the file without having acquired it first. I mean, the only real tricky case here is make clear exclusive Fcb list. This is a rather tricky piece of code in the first place. So what we'll do is we'll just indicate that it modifies the resource for the first entry in the list. We're not going to try to model the whole list, just the first entry. And the way in which you can interpret this is just like if you see a call to a function which has this annotation, then it's just saying that unless I know that a particular file is not on the exclusive Fcb list, there actually are some ways to indicate this. Then the new value of that lock could be anything after the call, including 0. So it's not safe to access that file's data anymore. You have to reacquire it. So this defines our 4 annotations, and we want to use these in the previous example to make sure to add this first check and make sure it passes, and to add the second check and make sure it fails, which it should. So we're just going to go from the top down, just go through each of these functions. So Ntfs acquire exclusive Fcb. We want to model 2 behaviors here. Let's have the prototype. We need to model 2 behaviors here. First, that it's a try lock. If it returns false, then it did not acquire the lock. It's not safe to access the file anymore. It's not safe to access the protected data yet. And so it acquires only when it returns true. So we'll use our conditional acquire annotation. It acquires the Fcb if it didn't throw an exception, because it can throw, as we know. We use this special thrown annotation, which Havoc understands, to indicate that. And the return value is not false. But there's a second property here, which is that if you can do a blocking acquire on it, just if you don't use the acquire don't wait flag. And so that's the second thing here. If you don't use acquire don't wait, then the function is either going to return true or it's going to throw an exception. You know that it must have acquired the lock if it's successfully returned. And we didn't write an annotation in the language to do this because this is just a plain old post condition. And we'll use the regular ensures to indicate this. If that flag is not set and I didn't throw an exception, then the return value is not false. And we can take this specification and both check the implementation of Ntfs acquire exclusive Fcb, making sure that it actually follows this behavior, as well as all the call sites. We can check and make sure that they correctly acquire the Fcb even when they're doing try locks or doing any combination of flags which they passed in. So let's move on. So we have this assignment here. We want to make sure, this is actually a macro set flag. It's just doing a write to that location. And we want to make sure that the Fcb's resource is held at this point. And again, as we saw with the ref count, we want to make sure that this resource is held every time the Fcb state field of an Fcb is updated, not just this particular point. And we'll use the instrument directives for it, the same mechanism we use for the ref count. And we'll write this here. This is saying we'll use an instrument write, which will basically put in a call to this function every place you see a write in the code base. And we'll use the requires FCB exclusive annotation to add the appropriate precondition. So we get this call here, and since we modeled acquire exclusive FCB correctly, we can verify that this check passes. We've actually checked that this code is correct. Let's go down here. So NTF has verified fixed file record. As we saw that it released every FCB that's been acquired up to this point, but it does it through a fairly deep call chain. It's actually 7 or 8 functions deep. But once we know that it might actually release that, then we'll add the make clear exclusive FCB list annotation on this function. And similarly for update FCB and SCB, that this guy can call NTFS update FCB info from disk, which will do unprotected writes to protected fields in there. So it must be the case that when you call this guy, you're holding that FCB exclusive. When we
So those two annotations were inferred automatically?
Yeah, that's the next slide. Sorry. When we have these two annotations, then we have enough information to fail this check. We'll get the error here because we're not sure if that FCB is still held or not. We want to point out that, verified fixed file record, it seems very unlikely that it actually will do this, so it would be very hard to pick up. It's not even clear where the bug is. There's an inconsistency in the code. But we can use the tool to pick these out. The question is, we had these deep call chains, and there are several hundred functions that follow these behavior. We need to infer these two annotations, make clear exclusive FCB list, and requires FCB exclusive. So the clearing functions, this is pretty simple to find. It's just anyone who transitively calls release all resources and the related functions. There are actually a number of functions which will do the primitive loop through the FCB list and release it. And then for the require functions, is that what we'll do is that we'll find all functions which are always called with their FCB parameters held exclusive. That we can just instantiate our inference with every time a function is called with an FCB. And that will give us the correct cases as well as the cases, but it won't give us the case like in the previous slide where the function actually might not be called with the FCB held exclusive. So for that case, we will have to fall back onto manual annotation. But the nice thing here is that we've inferred the annotations for the hundreds of correct cases, so we don't have to go and look at them by hand to figure out what's going on here. And so the results for the FCB resource, and we've only really presented a very small piece of this puzzle. The FCB resource is one of the core data structures in NTFS, so it's related to all the other core data structures in NTFS, like the volumes and its children's streams, incoming links, and so forth, and which we're not going to talk about because it's really complicated. But we found about 25 bugs that were just sort of broadly related to the FCB resource in general and to all the other supporting infrastructure in the code, as well as inferred these FCB-related properties. You had the 200 functions that might clear the exclusive list, and the several hundred functions which must always be called with a particular file held at entry. And let's see. I guess that's the end. What we're really trying to show here is, it's the amount of work that was required to find the FCB resource bugs. It was really several weeks to understand the code base to figure out which functions took files that are held. But it seems that we got a good payoff for it. We found these bugs which are very hard to find through other means, and especially either statically or dynamically or with testing and any mechanism that we have. And we tried to build up this roadmap that seems to work well for finding these properties, and we're hoping that it will work for other properties in other systems. We're doing other work to check both properties inside and outside NTFS, looking for deadlocks, which is a huge issue for NTFS. We're getting some partial checking there. I think Shuvendra just reported a few possible bugs on that front, as well as looking at more general device-specific properties of other code bases. And we're hoping that the NTFS team will pick this up and start to use the tool in annotation. So we're trying to slim down the tool just to a point where, as a nice simple interface that a developer can pick up and use to specify their own properties. How's that? Yep.
You said something that you don't look across threads. So is that to say if let's say I allocate something and then I queue some work item to some other worker thread that will later free it, will that get flagged as a leak? Because the one thread you're analyzing at a time doesn't show the free? Well,
since it's looking at the single procedure at one time, that you'd have to actually indicate what the correlations there are. That if you pass, if you're doing a leak analysis, then you'd have to actually indicate the post condition. In terms of in terms of understanding the effects of other threads, the main thing is understanding interleavings, or just what are the possible effects of other threads, which we're not considering.
So a related question is, you found $25, which is great, first of all. How much was the noise level? I mean,
What?
when you sit through?
I mean, so initially is that there were a couple hundred reports. I mean, the main thing with an annotation-based tool is that most of the warnings are due to missing annotations. It's either a place where you required a more specific annotation that you inferred. Say this FCB is only held if a particular combination of flags occurs. And I mean, you can either consider it as a false positive or just this requires extra manual annotation work to deal with. So it's just like in terms of the amount of programmer effort or developer effort to define these.
So then you see it as kind of an interactive thing, because you talked about being able to infer annotations. And so if the inferred annotation is more general than the quote real annotation, then I, the developer, go back and tighten it up myself?
Yeah.
Right, so it seems like, I mean, a sort of design principle or sort of common idea in the inference is to sort of identify the 90% case, which is sort of most of the functions will throw, or or most of the functions will balance their reference counts, and so you sort of err on that. You sort of get the inference to catch sort of the common case, and then where it's too over approximate, then the developer sort of has to say, oh no, it only throws in this certain case, or it's only incrementing the ref count in this case, otherwise it's balanced.
Yeah, I mean, what we want to do is we want to find the most efficient way to get the correct set of annotations, the one that actually fit the right abstraction. So if the inference will capture the most common type of annotations, and then you have the developer go in with manual annotations for the rest.
So once, I'm sorry, so once you have done the inference, do you think there's a need, what are the scenarios in which you need to redo the inference, or is it more incremental? I mean,
so an example with the FCB is that it's going to be looking for functions which are always called with a particular file held. So if you have a case like this conditional behavior where an FCB is only held if some flags hold, then the inference will fail to infer that precondition, and that can lead to cascading failures down the line. So what you can do is actually go back and fix that precondition and rerun the inference, and it will find, and now it will correctly reflect the callees. Sure.
So NTFS is unique in that it sometimes holds the resource and then re-enters the same thread, right? So that means that some functions which probably don't have these annotations that they're supposed to, now actually all of them hold the lock now.
Yeah, I mean, we're not really modeling the reentrancy very well. If you call out of NTFS, like if you go down to MM or so forth or have a page fault, then it will not, it's not modeling that correctly.
What's the next property you're going to go after, or you suggest that someone go after?
Okay. Well, I mean, the deadlocks in NTFS are a very big issue. It's actually a very, very complex property because you have to understand, it's not just, I mean, both in terms of expressing the lock orders as well as figuring out what a particular file even is. Because in NTFS is that they're both user files and system files. There's a special lock order for the different system files. But these are all just files. They're just pointers to FCBs. And you have to figure out when a particular file is a system file or not. So, that's one that we think that will be helpful for developers. I mean, in terms of future areas where I don't think the checking power really is there yet, I think one very interesting property is just, I mean, is the file system correct? Is it going to make sure that if you just crash at any point that it will actually be able to recover correctly? This is sort of like the transactional nature of the file system that's very important for reliability. But static analysis is not there yet. Yep.
How fast does this tool run? If I'm meant to sit there interactively refining my annotations, I don't want to overnight run. Is it? Relative to compiling and linking NTFS, is it twice as long, half as long?
It's several times as long. So I think so. If you're NTFS, I mean, it'll compile in a minute or so. If you try to run over the analysis over every function in NTFS, it takes about an hour and a half, which is pretty long. But if you're doing the refining loop, you're only interested in one function at a time. So you can pick that. And it's generally just a few seconds for most functions. It is plugged into OACR, so you can pick it up fairly easily.
So is this work going back into commenting in the function? I feel like this is great work, right?
The comments are fine already, Robbie.
The comments are not fine, I think, right? I mean, how does this loop back into the developer writing the right code the first time? Because these annotations actually go into the code when they're checked in, or?
So what we did with Ntfs is that we didn't modify the code itself. We added them on the side. But the intent here is that, is that these annotations keep going back. There. So this annotation here really should be going at the prototype, so that it's basically a checkable comment for when this function acquires that resource.
Because I find that if a new developer inherits Ntfs, which is a huge code base, it'll be good to take all the stuff out of this and actually know up front that this resource is being held or not being held, rather than do the.
But we're looking at, because he did everything in a separate header, of merging that into the mainline headers. You don't have to change the code, you just have to change the prototype definitions. We're looking at moving that into the mainline code for Windows 7. It's just biggest issue is just resources to do it.
Just following up on that a little bit, not these annotations, but another batch of annotations is also coming in through the work on driver stability. And we're definitely going to have to be talking, as Jason and those guys know, about the details. But what we're finding is fairly consistently you end up with some initial developer resistance to putting these annotations in until they've actually seen some real examples, and then it usually flips the other way. So it's a matter of getting the annotations in there to get them looked at. Will, I think, in fact, turn a resistance into a pull.
But you need the annotations to actually to be beneficial. You need to get more benefit out than the work that you put in. So if you have a nice lightweight set of annotations, then that's the best situation.
I claim that the biggest issue
It's not that developers are resistant, that we're not allocated the time to do it.
You and I should
Existing
talk
SAL
offline
stuff that
about
was
that.
done for Vista, many people thought it was a fine idea, but to give us an unfunded mandate to say, put these in, but we're not allocating any time for it, we have all this other stuff to do, was a huge issue. And I think you get more resistance for that than anything else.
The other thing, just to be totally frank about it, is SAL for us in Ntfs didn't do a great job of finding the bugs that we have. Havoc looks a whole lot more promising because, as Brian said in his introduction, this is tailored to finding the cases we have, and so even though we still have the same cost to annotating our code, we've got a much bigger win on the other side.
I mean, you can look at it as sort of, a much more thorough form of testing directed at very specific properties. And I think, what we'd like to see in the long term is people really thinking about having, as addition to their testing budget, having a little verification budget, right? I mean, to have some time to devote to the annotations, to have some time to update the annotations, keep them in sync. Because what you're essentially getting in the end when it does this whole tool chain back to the theorem prover is, for acyclic code, it's testing each path very completely with respect to that property. So for these critical properties that are really essential to the functioning of the code base, I think, we'd like to see in the systems code that people start to think about, budgeting for that and having, we obviously need the tools to support things like Inference, but I think, with OACR and SAL and this future work, we have a tool chain that, people can do much more comprehensive sort of validation of their code. And then it's documentation, so when new people come in, they're about to, call this function, they look at the header, they say, oh, this could throw in that situation, I didn't know that. So it brings up to the level these issues.
SAL annotations, prefix directly benefits from them, prefix which run regularly, right? Prefix runs regularly and prefix runs all the time. What is the process for running this? I mean, is this a purely developer-initiated thing that you would once in a while run on this, or
I think it's like SAL. It has to. It's going to go into OACR. It's a plug-in for the OACR, and it has to be run regularly by the developers as they change the code base. Otherwise, things will get stale. Brian has more experience with this.
Well, that's okay.
What's the plan? That the developer would once in a while run this?
No, it'll be part of the OACR check-in. I I mean, every time they modify the code, it'll be low.
Yeah. I mean,
That's,
yeah.
at the function level, it just takes, I mean, for single functions, it's quite fast. Right, so if you're modifying just a single function, it'll complete it.
But the OACR tools are running on file by file, so.
Yeah. It'd be nice if we could
function by function, it's running
but
changed files.
But only changed files.
Correct.
Yeah.
And that's assuming all the annotations are in there. The big effort in all of this is we have a component with 400,000 lines of code in it. It takes a long time to put this stuff in there and get it right. And the way release cycles are nowadays, they don't allocate a lot of time for this type of stuff. And so maybe upper management ought to, think about that. I mean, these are great tools.
Yeah. So it's great to see Ntfs is taking the initiative, but I was wondering more like, memory manager can easily use this. It's a big code base also, 40,000 lines of code, right?
I mean, the hope is that you have another code base that has its own properties. That is just to take what we did here and map it to the new properties. And we just want to get the right process for doing that, for getting these annotations into the code and getting that checking.
I had a follow-up comment on what Tom just said. I think the allocation of resources to verification engineers, I think that move has already happened in hardware companies like Intel, for example. They have design engineers, they have test engineers, and they have a group of engineers called verification engineers, which try to apply these kinds of tools to the hardware designs.
The shell team experience is that there are some developers who champion the SAL annotations, and they drive the more thorny issues that require a lot of in-depth analysis that not every developer is expert in. And from my experience, that's been pretty effective for driving SAL annotations and getting the code to green.
So just a quick update on related but separate efforts. So we have an initiative of extending the SAL annotations, targeting specifically for locking rules and some of the resource issues. So it's called concurrency SAL, and it's probably going to be
Who's we?
This is from CSE, Center for Software Excellence. And it's going to be available as a prefast plugin pretty soon, like in a week or so, actually the 7th. And we also realize that it's a lot of effort for putting the annotations into the code base. So that's why we have invested heavily on Inference, trying to automatically infer a lot of the locking rules and locking properties, so that the goal is that if the developer wants to just find some valid bug without spending too much effort, they can just turn on the toolset and run very automatic development.
Does it require any annotation to be added?
Eventually, it's like the more annotation you add, the more coverage you will get. But to get the initial benefit, you don't need to add any annotation. You can just start running the tool, and you can find race conditions, resource leaks. And our intern Anna is going to give a talk tomorrow talking about the inference work. If you're interested in by the way, Brian has interned with us 3 years. For 3 years, so he's fairly familiar with all the inference work. Brian has been instrumental in inferring the SAL annotations for buffer overload.
So have you tried looking at the basic lock packages we have, right, and starting there as opposed to using code bases and working backwards?
This Brian's work for Ntfs is kind of complementary because he targets a lot of more. The annotation here is more expressive, and where our concurrency SAL work is fundamentally targeting locking-related issues. But I guess most of the work can be viewed as using similar approaches, but the underlying analysis is different.
I think there's probably a unifying theme here of resources and basically tracking resources through the code, and then also tracking which locks are associated with the resources, and that probably is endemic to most systems code. That one needs to do this sort of thing. So the reference counting should be that sort of template should be reusable.
Yeah.
Actually, does your inference engine that you're doing, does it deal with rays?
Yes.
So it does recognize rays and handle that?
Yes.
I wanted to ask how customized the inference step was for the NTFS work. Did you, if it's going to automatically annotate things with your macros, that means you must have had to do some kind of custom inference rules.
Well, it's since it's wrapped around the checker, the main thing here. Let's go. The main thing that the inference takes as input is the annotation it's trying to infer. So in this case, what you do is that you specify an inference function which has the annotation requires FCB exclusive, and then it'll basically populate that across every function which takes an FCB and try to prove them all and remove the ones that it can't. So in terms of the customization, is that it went away? In terms of the customization is the annotation that you supply, which defines the population that you're trying to infer.
But the inference mechanism is generic.
It's generic, yeah, because it's all wrapped around the checker.
So Brian,
yeah.
You mentioned that for the call-site effect, you're concerned that the mod-site analysis could be too huge to track. Have you considered using some slicing techniques by just focusing on some related variables?
We thought about it, and we haven't pushed too far on that, but that seems the most promising route, is to figure out which fields are actually relevant to the property. I feel like, say for the FCB reference count, there are only a handful of fields that are relevant, and if you only track mod sets for those, then you could get some traction.
Our experience shows it's quite feasible. Focused mod set analysis.
Yeah, the thing that's the most important is to capture out parameters, because these are places where you pass the address of some local, and you have to know that thing changes, or else you're not modeling what the caller is doing right.
There was one point that I think didn't come across very clearly, which is that the analysis is sound with respect to modification of the resources. So those are being assumed, but they're also being checked also inside the functions. It's only unsound with respect to modifications, checking of the mod sets of the actual heap. Right?
Yep.
Okay. Sorry, I didn't get that.
So what Brian did is he takes the actual program and he instruments it with updates to these resources. So while the checking is unsound, meaning with respect to the modification of the heap, it is perfectly sound with respect to the modification to the values of resources, which is very important because the resources, the state of the resource is very crucial to capturing the property.
So I should probably follow this up offline with you and Tom and some others, but can we use this to record not just when a violation has occurred, but when there is a violation delta, meaning that if there are things that we haven't annotated correctly, so there are known issues in the code already, we can still detect a case where somebody checks something in, which increases that. I mean, if you've looked at how
which introduces a new error.
time build -verify, for example, it's very effective at getting value out, even on the code base that hasn't been fully annotated.
That has or hasn't?
That hasn't been fully
Okay.
annotated. I mean, is there any way we can use this tool in a similar way?
I mean, you should be able to. I mean, since it's just an OICR plugin, it just consumes annotations. You should be able to reuse most of the same infrastructure.
But the noise is what's going to deter. People
Yeah.
find it noisy, they not turn it off completely.
Mm-hmm.
It's will be no use after that.
Yeah.
Right?
I mean, a lot of the noise comes down to designing the property itself, because you can actually design these properties that bake in a fair number of assumptions into the code to reduce the noise. One area in NTFS where that's important, there are many important aliasing and variants with neighboring objects. Instead of trying to prove that these hold, we just assume them.
One strategy for reducing noise is to disable the noisy warnings for most developers, but then have the champions enable them and have them try to reduce it until it becomes acceptable.
Mm-hmm.
You can turn it on again.
Yeah.
Or use the delta thing to at least catch violators.
I think what it comes down to is that if you think that this kind of checking is valuable, then you need to have some resources devoted to a verification engineer who is willing to tolerate the noise and interact with the tool in order to suppress, by using annotations, that noise, so that it becomes more palatable to the developers.
One thing that we really should point out here, though, is that, I mean, since the checker is really modeling exactly the behaviors of the code, if it's not so much noise as a missing annotation, that it's just trying to figure out, well, what are the annotations I need so that this thing understands the code well enough. Yep.
So
And related to this and the noise and the precision of the analysis itself, you mentioned that the underlying analysis is a precise analysis of loop-free code, but actually it's not really an issue here, right? Because at that level of abstraction, for instance, you don't have that much noise due to the imprecision of the static analysis, the constraint solving. Is that correct?
That's it. Well, the question is like some of these functions that can be thousands of lines long have millions of pass-throughs. I mean, you need an analysis that actually models exactly what's happening, that doesn't try to merge any information at all or at points and just start to lose data, which is how a lot of static analyses can fail.
And so it's a black point pass-sensitive analysis that is being done,
yes.
And it's important to get this right because this depends really on the pass type of properties, or you could just be pass insensitive, for instance, and be as precise.
You really need to be very pass sensitive for many of these. There are many times when you use flags in the code to set particular state, which you'll check at exit. You like say I acquired a resource, set a flag, and then go down to the exit, the sum finally block, and then it'll test that flag. If it holds, it'll release the resource.
The Ntfs code does include loops, for instance, perhaps function pointers. Is it inline assembly code? I don't know exactly what's like.
There's not really so much inline assembly or function pointers. I mean, loops are a concern. We did have to write some loop invariants. They were generally very simple, just like whenever you return to the head of a loop, some particular variable is false, and that's the majority of them.
I would really love to see a re-entrancy model. It will help the total land quite a bit. Because there are all these drivers up there who are now guessing when locks are held or not held. You know? It will really help them to know that Ntfs is holding this, therefore I can't do this.
Okay. Yeah.
You mean modeling the re-entrancy into Ntfs when you go, okay.
Yeah.
And are those
On
locks?
the same thread.
Okay. They're global locks or they're locks per file, per FCB?
I'm not that familiar with Ntfs. I just know that there are locks being held. Some might be global, some might be a volume, some might be FCB. There are locks held in certain situations which cause deadlocks in the stack.
So because of this re-entrancy, are you more worried about the deadlocking issue or about race conditions?
If we know that these locks are being held on re-entrancy, there are cases where they're held. Ntfs is supposed to know all of that correctly, but if there are bugs in there, it would be really nice to find those out.
But I think what you're getting at, right, is cross-component deadlocks, where we have in the I/O stack a particularly crazy ordering model where you can be called from a filter burst calling Ntfs or Ntfs, which faults into a filter, right? And
But
so
if you find this out, then it won't help finding the actual deadlock, but it'll just help in saying that this function can hold
This is the documentation.
off, right? And it can re-enter.
So for documentation.
Therefore, now you know it can re-enter and hold a lock. Therefore, I don't want to issue a call.
The UI teams are also concerned about re-entrancy, mostly around resource lifetime issues. It's important to know which functions can re-enter and which ones can't.
Yeah, I think re-entrancy in general is a huge issue, but I mean it's not quite clear from this how to handle it yet. Anything else?